Welcome to this fifth set of lecture videos for Physics 4C. We finally start our coverage of physical optics, also known as wave optics, looking at the interesting results that come about as a result of the superposition principle and wave interference. We start with a quick review of wave interference using the example covered in Physics 4A, standing waves. This review is meant both for those whose Physics 4A class did cover waves but need a refresher on the mathematical treatment of the wave phenomenon, and for those whose Physics 4A instructor may not have covered the waves. Then, we are going to spend the remainder of the lecture looking at a first pass analysis of double-slit interference, starting with the demos, and then defining the idea of phase that we will use in double-slit interference analysis, as well as other wave interference analysis in the future. And finally, ending with the double-slit interference analysis, deriving the constructive and destructive interference conditions. We will come back to the more mathematical aspects of the double-slit interference phenomenon in the next set of lectures.
So what I want you to, for the remainder of today, is set the stage for what we are going to do in the next week and a half. So on Thursday, we are going to talk about something called the double-slit interference. It's the simplest kind of wave interference that we'll look at in this class. And what that is it's a starting point to talk about something called the diffraction later next week. And the reason diffraction is useful is it tells you about some fundamental limits to the performance of optical instruments, which is called the Rayleigh criterion. It establishes something called the diffraction limited resolution limit of a telescope. So this is going to be a common recurring feature in Physics 4C. So in earlier physics classes, we had this attitude that ideally things could be perfect. Ideally, you could have a frictionless surface. Ideally, your measurements could be arbitrarily precise. Right? Ideally, we never exclude that. In Physics 4C, we are going to start talking about fundamental limits, as in some limitation to what we can do that laws of nature itself says that we cannot do. So when you have a certain size of a telescope, there's a fundamental limit to how small an angular distance that telescope can resolve. That's determined by something called the Rayleigh criterion. We're going to talk about it in about 2 weeks. So I just want you to put that there as a reason why we are going through all this math and interference stuff. It does have a practical application to it. It allows you to calculate those fundamental limits to how ideal instruments work. Okay. So this is more of a review of what you guys already did it in Physics 4A. The first time I taught Physics 4C a year ago, I thought I could do without having to do this review, save a little bit of time. Then I discovered most people forget about wave stuff in the 1 semester since you're Physics 4A. How many of you remember the wave interference from Physics 4A? Yeah, and half of you were my students. Wave interference. Tell me what you remember about wave interference. What are some of the things you can, what are you talking about when we talk about wave interference at all?
Destructive and constructive.
Okay, some people remember the phrases. Destructive interference and constructive interference. So what's happening when you have something that you are calling constructive interference? What's happening when something like this happens?
Amplitude increase.
Okay, amplitude increases. You can sort of look at it like you have a wave and you, let's see. When you have more of one thing, then you have more of one thing. Sort of like, I don't know, this is going to be some strained example. It's like when I have one tennis ball, I have one tennis ball. I add one more tennis ball to it, now I have two tennis balls, right? So in some sense, constructive interference is sort of, it somehow matches better with how you deal with the things that are not waves. Let me use this simulation to actually give you an example of constructive interference. So I have waves on a string, and with this simulation, this is what I can do. I can take two wave pulses and add them together. Let me just do it this way. I happen to know this is what works well. Slow motion. Let's see, shortest width. That's probably good. All right, so there's a wave, and I add another wave to it. Oops, sorry, no damping. All right, one more time. I have a wave there, wave, add another wave to it, and you see that as they come together, and when they get together, they get bigger, right? So that's a constructive interference. You add two waves, so you could look at it almost like you have one wave, and you add another wave on top of that, and you get one wave that's bigger. I don't know, sorry, that sounds a little bit too simplistic.
Isn't that the superposition principle?
Yeah, that's what we're gonna get to. So how do you get destructive interference? This is the one that where there's non-wave. There is no non-wave analogy to it. It's sort of like, you know, I have one baseball. Is there a way I can add another baseball to it so that they disappear?
Antimatter.
Yeah, that's a whole another matter. So with things like objects like tennis balls, there's no way to add them together in a way that they would appear to disappear. But with the waves, you can. In fact, I don't have to change anything here. I can just let it run for a little bit longer, and you will see it there. So I have a wave that's coming in, that's right side up, and a wave that's coming, that's wrong side up. And you will see that as they overlap, they disappear. So it almost appears as though it's gone. So, you know, the simplistic description of destructive interference would be, I have a pulse that's negative, plus I have a pulse that's positive. Add them together, I get flat line. But that's a bit simplistic. It's there's a more sophisticated description than that. And here's a question I guess maybe you should, I think you might be able to answer based on intuition, which may be right. So right now the time is paused. What do you think will happen when I let time go again? Keep going? I mean, right now there's no wave whatsoever. Why would the wave suddenly reappear when I let time flow again?
Because the energy is still here.
Yeah, and your intuition is right. So I had a downward pulse that was moving to right? And I had an upward pulse that was moving to left. Watch what happens when I let time flow again. Those pulses simply move through each other as though they weren't there before. So if you're just tracking this pulse here, how it moves, you can ignore this pulse altogether. And this will just continue to move the way it always does without any care for the other pulse. This is the most basic thing to understand about wave interaction. How one wave interacts with the other is that they don't. The motion or movement of one wave is completely unaffected by motion or movement of another wave. It's a linear phenomenon. If you are taking linear algebra, you might have covered something called the linearity. So all of this is coming out of those mathematical properties. In physics, we call this is where that name comes from, superposition principle. And I like to say that we give it such a grand name, superposition principle, because what it says is really simple. What it says is that when these two waves overlap, they don't interact with each other. So if you have, let's say this wave can be described by function f1 as a function of position and time. And let's say this can be described by function f2 and function of position and time. When both of them are happening in the same medium, as indicated by this plus sign, they are going to be overlapping in space and time, right? And when you look at a string, a given section of string can be at only one position at any given point in time. So when these two waves overlap, there is really going to be only a single function of position and time. And what superposition principle says is that the way you get this is the simplest mathematical operation possible. You take this, and you simply add them together. So this is f1 xt plus f2 xt. Yeah? So everything else we are going to talk about with wave interference comes from this. So we have a source of wave, which is producing some wave. In case of light, this will be a wave of electric field. And we have another source of wave. And when we consider the combined effect of those two sources, we simply add them. We don't do anything to anything else. And if you remove one of the two sources, then whatever effect the first source would have produced is still there. Now, what is interesting, and sorry, I'm making this sound very boring, but that's why I'm glad some of you mentioned the destructive and constructive interference. You do see interesting patterns. And these interesting patterns you see are the result of working through this math. So I guess maybe as a way of review, I should remind you of one of the examples of the wave interference. One of the examples of wave interference. So in physics 4a, you should have covered two examples of wave interference. One is a standing wave, and the other is a beat, as in acoustic or audio beat. I don't know, well, beat as in beat frequency. How many of you here remember the phrase beat frequency? Okay, not many of you. Well, this is people who took my class, some of you do. Not all of you. How many here remember hearing something about standing wave? Really? Do other physics 4A instructors not cover waves? Okay, well, they should have. Let me do this much. So I guess if I told you, I think, so here's the nice thing about wave. You can talk about wave as a purely mathematical idea. It doesn't even have to be physical. I mean, when you look at wave on a string, there is some physical law describing what's happening here. That's why, when you change the tension, that changes how these waves behave. But at the end of the day, you can describe waves as purely mathematically. So let's take that point of view. You can, if I told you that there is a source of wave here, that's a sort of source of it's generating some mathematical function, I can tell you that this is generating a sinusoidal mathematical function. So something like this. That makes sense? Like nothing unusual there. What function would you use to describe this function that you are seeing? So right now you are seeing it as a function of time, and you can imagine freezing it in time and describe it only purely as a function of position. So right now, what you are seeing would look like a height of the beat as a function of the x location of beat. And right now, you could say it's at time equals 0. Or if you allow time to flow again, then it would be y as a function of position and time. What kind of function, mathematical function, would you use to describe this? Something like sine, right? So let's say it's a proportion, or it's time, some amplitude times sine of, and it's this portion that you have to work out. So this portion will need to have position and time in it.
Kx minus omega.
Yeah, you might have this memorized, in which case it's good. How many of you remember seeing something like this? Let me do a quick introduction of all these parameters, which might be new to maybe a third of you. A, amplitude, that seems good enough to everyone? Okay. What's probably, I mean, x and t, those are your variables. What's new to you is omega, even omega might be reasonably familiar. This is angular frequency. So omega angular frequency is 2 pi times frequency, or it's a 2 pi divided by period t, right? What's probably unfamiliar to people who are just seeing waves now is this k, or what we call wave number. So let me just write down the definition of wave number. So the wave number, k, is it's 2 pi divided by wavelength lambda. Everyone here knows wavelength lambda, right? You know what wavelength is? That's length from here to, length from here to here. That's the wavelength. So, so the best way to look at this k is it's similar to omega, except in relation to position. So t is how long of a time it takes for a wave to repeat itself, right? That's the period. Wavelength lambda is how long of a space it takes for a wave to repeat itself. So the way you define angular frequency in terms of period is similar to how we define wave number in terms of wavelength. So that's the explanation of this parameter. I guess let me try to give you this much intuition. So let's say, let me freeze it in time. And this is the claim I want to make. I want to make the claim that this expression already tells you in which direction the wave is moving. This expression already tells you that the wave is moving to the right instead of to the left. So for those of you who are in my physics 4A, hopefully you remember, I think we spent enough time on this. Many of you were not in my physics 4A. So this is how I reason this through. Let's say I take a particular point on the wave. It doesn't have to be this point, but it's a convenient point. I take this particular point on this on the wave. Do you know what the value of sine of whatever is inside should be equal to for this point? Well, so the sine will be 1, right? Yeah. Okay. So that's 1. So, and as this wave moves, there is a point that's at this point. So at some later point, if you are looking at this same point in position, then it's not at this value anymore. It's no longer right? But there's another point for which you can say sine of whatever it is still equal to 1. And when you are looking at movement of wave, you are really tracking this movement here. So for you to keep track of the same point, whose value of sine is not changing, what you really need to be able to say is that whatever this value is, I guess pi over 2, this value has to stay constant. Good? So this has to remain at pi over 2 for this to be true. So as you look at this expression, you imagine this. As my time increases, so I'm moving forward in time, how should my x change so that this combination kx minus omega t does not change? So as time increases, should my x increase or decrease? So that this whole thing stays constant. Decrease, look at it again. Increase, right? Because of this minus sign. Yeah, so that's why this is telling you that this wave is moving to right. Imagine I had it reversed. Imagine this was instead of a plus sign. In what direction will wave be moving? the other way. Because then now you will say as t increases, x has to decrease to keep this constant. So I guess that's the quickest introduction to traveling periodic wave I can do in the time. So I want you to introduce this so that I can talk about at least the standing wave as a way of reviewing about waves and wave interference. The wave interference we are going to cover in this class, it's going to be slightly more complicated. So in physics 4a, unless you took it with someone who covers more material than I do, you didn't look at any wave interference in more than one dimension. This is a one-dimensional wave. So what we are going to do in this class, we are going to start looking at waves that are traveling in 2 dimensions. So we'll look at path lengths in 2 dimensions. So I want you to review the wave interference in 1 dimension so that when we move on to 2 dimension, at least some of the concepts will seem familiar. So let me actually set up a standing wave here so that you can kind of see it. I usually try to do this as a physical demo too, but I don't think there's time for it. So to have a standing wave, so I will never get a standing wave with this setup. I need 2 sources of wave. I need 1 source of wave that's moving from left to right, that's going to be coming from here. And I need another source of wave that's coming from right to left. Now, in this program, there's nothing that's generating wave here. But what I can have is set an end here so that the wave will reflect from this end and come back. Good. Let me just reset because there's a little bump there. Now, when you just set it like this, you won't get a standing wave. Like you look at it for a while and it's going to begin to look chaotic, but you'll say, all right, it's chaotic, no pattern of any kind. So let me do something that will help me get an actual pattern. So I need to first measure some stuff. Let me go back to pulse, restart. Pulse width, okay, I need a timer. Start the timer. It doesn't start yet because it's a timer for the simulation time. Okay, I'm going to generate 1 pulse and then just to see how long it takes to get there. 1 pulse, pause here, and gingerly go to when it just barely reaches that point. Okay, 1.18 seconds. So in terms of frequency, it's the reciprocal of that. So let me do that. 1/1.18, so 0.85 hertz. So I feel like 0.85 hertz is going to be a special frequency. So let me set it to be 0.85 hertz here. And let me tell you one more thing. I feel like whatever effect I'm going to get is going to be huge. So let me set a very small amplitude. I don't feel like I need a very large amplitude to get something huge. All right, that's probably good enough. And I don't need timer anymore. I probably need a normal time. It's going to take too long otherwise. Yeah, let me erase this while it's getting going. So this is what's called a standing wave. It's also called resonance. How many here are familiar with the idea of resonance? Yeah. So resonance. So you get resonance whenever you have a standing wave on something. This is how bridges get destroyed by strong winds. If you said there's a Tacoma Bridge or whatever, you might have seen video of. So now it turns out you can, there are other frequencies where this standing wave can be set up. You can do this at half the frequency. So 0.4, 43, let me do 43. 0.43 hertz. That also gives you a standing wave. And actually, for this setup, all the integer multiple of this will give you a standing wave. Let me just do one more. So it'll be 3 times this, so 1.29. Yeah. So with the different frequencies, the exact pattern is different. But all of them share some similar features. They all have points that barely move. Those are called nodes. And some nodes are nodes by physical reason. This is a node because this clamp prevents anything from moving there. Yeah, sorry, that's just, I think 1.28 might actually work better. So the end point here is a node because it's not allowed to move. End point here is a node because I set my amplitude very small. But some of the nodes, like these nodes here, there's nothing physically holding anything there. They are nodes because of destructive interference. That's what I mean. Wave interference is more interesting than I made out to be at the very beginning. So actually, let me work through the math using trigonometry. And next week, I can redo this derivation using complex exponential. Then it'll have a little bit of a point then. So this is how you, sorry, let me go back to 0.85 hertz. That works a lot better than any of these. So this is how we mathematically describe this standing wave. We look at it as a superposition of two waves. One wave that's traveling from left to right, and another wave that's traveling from right to left. And they are timed in such a way, they have a wavelength in such a way so that this pattern exactly fits. But so let me start out with that. So this is the mathematical description of standing wave. So for the wave, on the one single wave on this medium, you want to describe it as a single function as a function of position and time. And my claim is that this can be done by describing as a superposition of two waves. One that's traveling to the right. So that would be what you saw before. So some amplitude times sine of kx minus omega t plus another wave that's traveling to the left that has the same frequency and same wavelength. So let me write that down. Plus same amplitude times sine of kx plus omega t. Now let me ask you this question. As you stare at this mathematical function, does it sound right to you that this shape keeps changing? It's because this is not the exactly correct frequency. But so you see this shape that you see, sinusoidal shape with amplitude changing up and down, not moving anywhere. Does this obviously look like what this should look like? Really? Like as you look at this function, it's obvious to you that there's a point that never moves at moments in time. Not really, right? So this is what I mean by mathematical derivation, or mathematical description. We are going to take this mathematical expression and we are going to rewrite it in a way that as we look at the resulting expression, it's going to be clear to you that yes, that function actually describes this. And what that function will look like is this. The function that describes this, function of some position and time, it's going to look like a product of sinusoidal function of position alone and sinusoidal function of time alone. It'll look like sine of kx times, let's say, sine of omega t. It could be cosine. I think it might actually be cosine. Sine? I don't know. It could be cosine. Sine or cosine. Like if you got this function, then is that clear to you that yes, this is what you expect to see? As in when cosine of or sine of omega t is 1, you would see this shape. When sine of omega t is 1, you would see this shape, right? Sine of kx. And at some later time, when, I went past it. Well, when sine of omega t is minus 1, you would see this. When sine of omega t is 0, when sine of omega t is 0, you would see this. So if you got a function that looks like this, then you can draw a clear connection between this mathematical description to the shape you are seeing, right? So that is the goal. I want to take this expression and rewrite it up to a point where it's a product of two sinusoidal functions of a single x or time alone. And let me try to do this as quickly as possible. I have only 10 minutes. I want you to do more. Yeah, let me do this quickly. I can do this in 5 minutes, and I can show other examples of interference here. So, all right. So in the interest of time, I'll just tell you what I'm going to use. I'm going to use the trig identity that I've been telling you guys in the last lab. I tell people this is the most useful trig identity. You should have this memorized. It's an angle addition formula. Sine of alpha plus minus beta is equal to sine of alpha cosine of beta plus minus sine of beta cosine of alpha. Cosine of alpha plus minus beta is equal to cosine of alpha cosine of beta minus plus sine of alpha sine of beta. I can tell you how often these identities are useful. And if you want to derive it from scratch, it's almost, for me, it's impossible. It takes way too much geometric reasoning. So I'm going to use this to simplify this. And you can almost see a natural way of doing it. This is written as sine of one angle minus another angle. So I can use this angle addition formula to expand it out. So let's do that and see what we get. When I expand it out, I get A times sine of kx, that's alpha, times cosine of beta, that's omega t. Yeah, cosine of omega t. And it's minus, so I should pick minus here. Minus sine of omega t, sine of omega t, cosine of alpha, which is kx. Okay, that's my first term here, plus A times, it's the same thing except this is the plus sign. So it's a sine of kx times cosine of omega t. This time it's plus sine of omega t times cosine of kx. And as you stare at this, I hope you notice that these two terms are the same, exactly. And these two terms are exact opposites of each other. So when you add them, these two will cancel. And you are left with what we wanted from the beginning. So two of these, so 2 times A, 2A sine of kx times cosine of omega t. So I haven't really done anything. I just took this expression and rewrote it into this form. But this form makes it clearer that what the shape of the wave should look like this instead of whatever this tells you it should be. Yeah. So this is I don't know, a quick review of what you should have learned in Physics 4A. I guess oftentimes when you're taking Physics 4A, the wave appears to be a small part of the curriculum, and it, frankly is. But in this class, if I had to pick one thing that's going to be a constant theme throughout the entire semester, it's actually waves. It comes up with optics. It'll come up definitely with the quantum mechanics. And I can also introduce it into special relativity if I tried. And so this is a quick review. And the complication we are going to get in, so this is physics 4A material. I don't have any homework problem on this. If you need to review it, look at University Physics Volume 1. So what we are going to look at in this class is interference phenomena that you see with light. And with the light, standing waves here are kind of hard to get. I mean, you can, but it kind of takes a research lab level technology, Fabry-Perot. We're not going to do that. What we can do is we can start out with something called the double-slit interference. And let me use this demonstration to actually show you what that looks like. So this is obviously not light wave, but I can still illustrate the features of the interference with the light wave that you will see. So right now what you are seeing is, I don't know, wave from a single source. I have a source there that's being shaken at some constant frequency, so it's generating this wave that's coming up. And as you saw, the only reason it looks stationary is because the strobe light is locked. Okay. All right. So with this, you don't see any interference because you have a single source. Well, no interference. This is what double-slit interference looks like. Let me replace this. So by the way, if you are looking at it here, this is my single wave source. Let me replace that with the two sources that are going to be in phase, meaning they are going to be shaking together. So this is my two sources. Each of them will be like a single one of these, except they shake together. And watch what happens when I turn it on. Yeah, oh, I guess I must have set the frequency. So you get a pattern that's more complex and interesting than any one single one of them together. I don't know if I can, I cannot just stop one of them. I don't think I can reach in and do that. But do you see, so when you're looking at this region, where it's far away from the other source and it's presumably influenced by only one of them, you see that it's much like the other case, right? When you look at in between, that's when you see more interesting patterns. And to me, to us, especially as we look at it on Thursday, this is particularly interesting pattern. What do you see along this line that I'm dotting out? Do you notice anything along that line? You might call it destructive interference. So what you're seeing is that along this line, it looks as though it looks the same as when this was off, right? Just completely flat water surface, just along that line. And you deviate a little bit one way or the other, you get these wave fronts again. But just along this line, you get no waves. So yeah, this is the line along which destructive interference happens. And we'll look at the mathematics of this more, but this is how we are going to analyze it. Let's say you pick a point on this line. Then what you can look at this as is there's a wave that's arriving at this point from this source. And there's a wave that's arriving at the point from this source. Okay? They both have same wavelength. I could almost illustrate this wave this way. You know, this is the kind of, how am I doing this? I guess wherever there's black, I'm gonna have a cross. So something like this, I don't know. Sorry, I started out okay and then messed up. And there's a wave that's coming from here that looks kind of like that too. And sorry, I'm not drawing this right. And somehow the way they are adding up here, they add destructively. Whenever this wave goes this, let's say whenever water surface from this wave goes down, water surface from this wave goes up. Whenever this comes up, this goes down. We call that out of phase, and we'll, I guess, give a description for that a little bit more on Thursday as we work out the mathematics for double-slit interference pattern. But this is the mental image I want you to have, that when we are talking about double-slit interference or double-slit interference pattern for light, what you should imagine is here's a source of wave, here's a source of wave. They are synchronized. They are in phase. They shake together. And as they do, these oscillations, they propagate out to, it fills up the whole space. And for a given point in space, the effect here, let's say, call it the water height at this particular point, call that x naught as a vector, as a function of time. that can be described as a influence due to one source, y1, x naught t, plus influence due to other source, x naught t. And we are going to be able to figure out that for some of the points, these will be constructive interference. They will move together. For some of the other points, there will be destructive interference. Just the one change that I should make for the sake of accurateness for the next time is that for the light waves, we are not dealing with the water level. We are not dealing with the height of the water. What we are instead of dealing with is electric field. It's an electric field that we are dealing with. Because this is why it was important that we started this semester by talking about the light as an electromagnetic wave. So what we are going to spend some time talking about it is how the electric field of electromagnetic waves from here and electric field of electromagnetic waves from here will add together here in this spot in such a way. For certain spots, like this point here, they will always add up to 0 at all times. Or at certain spots, I guess like here, it'll add up so that it's at a maximum value. It'll still sometimes be 0 at a particular moment in time, but the amplitude will be at a maximum. Yeah. So let me first show you double-slit interference. I need the room to be a little bit darker. Wonder if I simply turn off the lights, it'll be dark enough. Let's see. So, let me pass this around. So I have a laser beam which is on a stand that I can just, put it on so that it just turns on the laser. Oops. So that it just turns on the laser. And I'm going to place this plate in front of it. It's a special made plate that you are going to be using in the lab next week. Let me just pass this around so that you can take a quick look at it. It has a bunch of slits made in it. And what I'm going to be using is, so when you look down one of the edge rows, there's a rows of two slits at different distances. So that's what I'm going to be placing in front of this laser to see what happens. So let me try to place this. And by changing the distance, I can use different slits. So let's see. So this is one with two slits separated by very little. In fact, I think that is actually essentially just one slit. Let me go up one more. So this is the kind of intensity pattern you see when you have light that's coming through two slits. I think those of you who are sitting up front can probably see it. The intensity pattern that you see is it's an alternating pattern of light, dark, light, dark. I have these things ready to show you on camera for those of you who are a little bit farther away. All right. Am I doing this right? Yeah, okay. So that's what we call double-slit interference pattern. Do you see the alternating fringes of bright and dark? Yes. So this is typical of interference, especially those dark fringes. That's taken as the conclusive evidence that light is wave.
Maybe as you look at the figure and you read it through, maybe it makes a sense. If it does, great. And what I think is sometimes helpful is to have a visual representation that's not a static image. I think it's a dissimulation here, wave interference. You can see from the picture that it kind of looks similar to what you were saying before. And this simulation has a few different representations to emphasize that it's The kind of thing that's described here is universal. So one representation we can use is a water wave. That's this drip, 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 this thing. And this is with the sound waves. And this is kind of visualized version of the pressure wave. Let's say black is high pressure, white is low pressure, and this is the expanding wave of high pressure and low pressure region. That's what sound wave is. Or a light wave. Here they use laser to illustrate. Or I guess that's not really laser if it's not focused at all. Laser that's passed through a very narrow slit. I think that there might be a way to describe it. So in a setup like this, on the screen, you would see something very bland. Like, like what you see on my hand. I have a light source here that's illuminating this hand that looks kind of flat. That's what you're gonna see on the screen with a single source. What you start to see more interesting things when you have more than one source. Then those multiple sources can interfere with each other. So, right now I just turned on one, so it does nothing. Or, it does something that's very boring. And now if I turn this off and I turn on the other, it'll also do something that's gonna look very boring. It illuminates the screen, it looks all uniform, nothing interesting. You get something interesting when you have two sources. And this is the interference phenomena. And in our description of a double-slit interference, what we are describing is places where constructive interference happens, and these are the bright fringes, and places where destructive interference happens. And there are some simple things you can describe how this interference pattern depends on frequency or the wavelength of light. When you have high frequency or short wavelength of light, the interference pattern becomes narrower, given everything else that's the same. And when you have low frequency or the long wavelength of light, the interference pattern becomes more broadly spread out. And you can actually see that in the expressions for the conditions for these. And yeah, this is, I guess, I encourage you to check out the simulation, play with it. It can be a good setup to illustrate some of the things that we try to describe it in words and put in our best effort, but sometimes words produce misrepresentation, or even when we use figures, sometimes figures can be misleading in certain ways. And the simulation is slightly less misleading in that it's interactive, it responds to changes, so you can do your own experiments. You can predict and check and do all sorts of stuff. So.
I just want to give you some conceptual ideas that you will need to work out the mathematics for Young's double-slit interference beyond just looking up formulas and using the formulas you look up. And the key idea that you are going to be seeing more throughout the semester actually is the concept of phase. How many of you here remember the word phase in a mathematical context? I don't mean phasing through walls. That's just X-Men. Okay, so let me just describe with this description of phase. I think the physical context that I want you to think about is an oscillation, something periodic happening. So you've seen mass on a spring, right? This is oscillation, something periodic. And this is the context where we define the word phase. And the concept of phase is useful for referring to different parts of the cycle. So I can define this cycle. I have some freedom in how I define a cycle. I can choose to start the cycle from here, midpoint. I can choose to start the cycle from the highest point, or I can choose to start the cycle from the lowest point. Let me make it easy for myself and choose the starting point as the highest point. So when I let go, this is the very beginning point of the cycle, and you know what one cycle looks like. It's all the way to the bottom and up. That's one cycle, right? So I could say that whenever it does that one full complete thing, that's one cycle. But I want to refer to it with more precision than that. What if I want to refer to half a cycle? Like at which point is it? At the bottom, right? And I can also refer to quarter of a cycle. That would be, first quarter, second quarter, third quarter, and then all 4 quarters. So, the concept of phase arises from trying to describe those different points of a cycle. So when you look at the phase of this oscillation, so each time it comes up to this point, each time it's at the same point on the cycle, it would have the same phase. This becomes a little bit more precise when you think about the mathematical description of this oscillation. When you look at, I guess, let me just call it definition of phase. So when you are looking at an example of oscillation, and when you want to describe the motion of oscillation mathematically, then what you use is you describe the height of a mass as a function of time, and it's going to have this form, some amplitude times, and the way I was describing it as cosine of omega t. So that at the very beginning of a cycle, or at the very beginning of anything, when t is equal to 0, it's at the highest point. And as time goes on, it starts by going downward, and then reaches the most negative point at some point, comes back to the highest point again. Good? Everyone recognizes this as the mathematical description of oscillation. So what we refer to as a phase is this. It's this part that we are referring to as a phase. It's the argument to this trigonometric function. So when we measure phase or when we describe phase, it's going to have a unit of angle. So you can describe phase in terms of angular units, like 0 degree phase, 90 degree phase, 180 degree phase. 180 degree phase is what we call, when we talk about phase difference, that's what we call out of phase. And so this is what phase is. It's a kind of an angle. And if you took physics 4A with me, I might have mentioned at some point, when you're measuring angles, there are 2 different kinds of angles. There's the phase angle, and there is the physical angle that you measure with the protractor. So pendulum is the most confusing one because so this is the pendulum. When you're trying to describe pendulum motion, you have to keep track of which is phase angle and which is physical angle. If you're looking at physical angle, it's never more than 30 degrees or so. But the phase angle will go all the way from 0 to 180 back to 0, 180, 360, 720, and so on. Good. Okay, so that's phase. And I guess to wrap up the introduction of the word, 10 minutes left. If you've seen the most general form of mathematical description of phase, then you might have seen this form. So what this is we call this a phase factor. And the word factor will be a little bit confusing at this point because I'm not multiplying anything. But that's what I want to explain next week when we introduce the complex exponential description. When someone refers to phase factor, that's what this is. Yeah. So with the phase factor, you can actually sort of change the point at which you are deciding the motion to start occurring. So I said, I just set this as my beginning point, right? At time equals 0, and that's where I got cosine. But with this phase factor, I can shift where my beginning point is. So if I choose to have my initial point of motion be when it's at the midpoint, then I would, maybe this should be a minus sign. Minus sign. I don't know, I sometimes get confused if it should be plus or minus. So then I would set this phase factor to be 90 degrees. Then if I set it to be 90 degrees, no, it is plus. So, okay, so let me, it's hard to do this with things in my hand, so let me draw it this way. So the way I was describing it originally, it was I have the motion starting from here, and this should be sort of 2 complete cycles or so, right? And so the way I had it originally was, this was the point where time was equal to 0. But maybe I don't want to do that. I want to say time is equal to 0 at some other point in this cycle. And I can control that by changing this phase factor. So this is when the phase factor phi is equal to 0. But if I say, let's say my phase factor phi is equal to 90 degrees, then think through this. So you start at the cosine of 90 degrees, which is 0, and you add a little bit of time, so that's going to tip it into negative side. So the curve that will look like, it'll look something like this. So 90 degree phase out of phase is kind of hard to draw. So this is the curve you would see with a phase factor of 90 degrees. And this idea of phase is useful because this is a way that we can describe any kind of constructive or destructive interference. So I have one oscillation. So you could say this is oscillation due to some disturbance somewhere, and it's happening at something like this. And let's say I have another source of disturbance. Maybe it's a string that there's a source of shaking at one end, and there's source of shaking at the other end, and I'm looking at the shaking at some particular point. So this is one source of disturbance, and I have another source of disturbance which has similar description, same amplitude times cosine of omega t. And if it's exactly the same, then that's kind of a special case. If you are trying to describe a more general case, you do that by adding a phase factor. This phase factor is able to describe a wide range of different ways of combining 2 different waves. So, so I drew, let me color code properly. Let me draw this one in blue. And let me just ask you what the wave should look like if we want the result of their interference, result of their superposition, to be destructive. As in, so I'm sorry, going a little bit ahead of myself here. So let's say the disturbance due to this source of wave, it looks like this, cosine of omega t. And you guys remember the superposition principle from last time. So superposition principle says if we are looking at just the total combined effect of these 2 disturbances, then the total combined effect will be just the sum of each individual effect, right? So let's say I want a destructive interference. I want a second source of interference, second source of disturbance, that when I add on top of this, I'm going to get 0. What does that wave look like? Yeah, upside down, right? It's not that complicated math. And this one is a little bit easier to draw, because I can make them cross at the same point. So when you add these 2 together, then the result of that sum, the result of the interference is that those 2 waves cancel each other out. And this is what we would call destructive interference. Now, here's the question I want you to ask. And this is the reason we started out with the phase. If I want you to specify this second source of disturbance that resulted in destructive interference, what kind of phase, what value of phase factor do I need? pi? 180 degrees? Yeah. So you guys are all giving me angles, which is good. Phase is an angle. So you could describe this as pi, or you could describe this as 180 degrees. And that would be one value. If you are looking for more than one value, then each time you add 2 pi or 360 degrees, you haven't really changed anything. So it'd be this plus 2 pi times an integer, or this plus 360 degrees times an integer. Okay? So with the idea of phase and the phase difference between two sources of disturbance, this is how we can simplify description of conditions for interference. So we can say to get destructive interference, we can say you get destructive interference whenever the difference in the phase is equal to pi or any plus any integer multiple of that, integer multiple of 2 pi. Okay? What if I wanted constructive interference? That would be where I add a second wave to it. So let me call that y3, where I want to add another wave on top of y1, but not y2, and plus phi3. What value should phi3 be so that I get constructive interference? 0, right? You want essentially add on top of this the same thing right on top of that. So for the so if you had something that looks like this, then this would result in constructive interference. Constructive interference. And the condition for that you can also specify with the phase difference again. You can say that to get this, the phase difference is equal to 0 is the easy answer. 0 is definitely a valid answer. And like with the last time, you can add any integer multiple of 2 pi without changing anything. So 0 plus 2 pi n. So I want to use this as the beginning point. And most of the analysis that we'll do, I guess on Tuesday. Sorry, I'm not able to actually get that far even. I didn't finish section 1. The big part of analysis we are going to do is based on some consideration of the physical setup, what kind of phase difference do you get? So we were talking about phase in interference last week. Let me call it function. Some kind of function is a function of time. And let's say you have an oscillation that looks like this. Something that you might have described as cosine function of time. Then there's you can have a range of possibilities, but I'm going to bring your attention to really 2 distinct cases. One where you have, so this is the function 1, and the first case I want to bring your attention to is where you have the second function that looks more or less exactly like this. Actually, let me, I don't know why I made this get bigger. Let me make it go smaller. So let's say something oscillatory that's getting smaller, doesn't really matter. All that matters is it's periodic, it has definite frequency. And if you have a second source of disturbance that's more or less moving at the same time, so when this goes down, it also goes down. When it goes up, it also goes up. Then this function would be described as something that has same amplitude times cosine of omega t. And this is how we want to compare periodic oscillations that are happening at the same time with the description of time plus some kind of a phase difference. And in this, the first case you are seeing here, this phase difference is equal to 0. And we have language for describing this. We call this in phase. Okay? And we looked at the other kind, that of case that you will also see today is it's when they're out of phase. So when the first disturbance goes up, the second disturbance goes down. And when it goes down, second disturbance goes up. So if I finish sketching it, it might look something like this. So I can describe this function also as, this would be the third function now, some amplitude times cosine of omega t and plus a phase factor. This is why I want you to focus on this phase, because so when you compare these different oscillations, everything will look the same, with the one thing being different. That one thing being different is this constant term, what you will see as constant phase factor later today. So in this case, what would be this delta phi for the second case? 180 degrees, right? Or I think at this point I do prefer to switch to radians. So pi phase, radians, or if you want to, you could call it 180 degrees. So you have that phase factor, and this is what we are going to describe as out of phase. And you know intuitively what these two different cases of interference leads to. You've heard these words when you took physics 4A. This is what leads to constructive interference, and this is what leads to destructive interference. Any questions on this? We went through this last week. Yeah. So I want you to pay attention to this phase as we are looking at different interference phenomena with light. So I guess I did draw the picture last week. So we did, it was last few minutes, so we didn't do any detailed analysis of it. But let's go over the double-slit interference. So this is the typical picture you see with the double-slit interference. And I guess the textbook has better picture than what I can draw, so let me start out with that. So this is, you saw the physical demo of this last week, and what we are looking at now. And this is the sort of the typical experimental setup. So when you have lasers, it's a lot easier to do. So you saw the demonstration with just a laser and a single double slit last time. And you will have a whole lab to work with this on Thursday, so I won't spend more time on that. But historically, the way people did the experiment was, first you have a single slit, so that you have a single source of light, so that light arriving here and here would be in phase. And these two now work as two sources of light that start out in phase, and depending on which location the light ends up at, they would either be in phase or be out of phase, and many of these dark fringes. So this is actual practical experimental setup that you may see, except your lab will be better because you're still using lasers. You won't need the initial single slit. Let's see. So, wow, this picture is still complicated. Okay, so this is the figure I want you to think about when you're conceptually considering Young's double-slit experiment. So you have a source of light that starts out. So you could say at at this location you can describe light this way. You can describe the light with its electric field. This sounds okay to everyone? You can describe light with its electric field. So you could say here, the electric field, just the component, not the vector quantity, just the component, as a function of time, is the amplitude times cosine of omega t. And I can say that because I'm describing the electric field at a particular point in space. So if I'm defining my axis this way, x and y, then it would be the electric field at x equals 0, and let's say y is equal to 0 here. So at y equals, I don't know, plus d over 2. Good? Yes. And the electric field here I could describe it as, so this is electric field 1, electric field 2. And electric field here, I could describe as the same amplitude. If we, assuming the intensity here and here are the same, the amplitude of electric field would be the same also. Times cosine of omega t. That's what we mean, these two are in phase. They have the same phase as they are coming out of this slit. And this would be at x equals 0 and y equals minus d over 2. Okay? And if you want to make it overcomplicated, you could describe the electric field at all locations in space. Anywhere the light can reach, you can describe the optical electric field. But let's make it simple for ourselves. We want to not overcomplicate it, make it simple. We only concern ourselves, what does the pattern of light look like at some distance L away? So we are only looking at the electric field at x equals L. But what it will be now is it will be a function of y. So let me draw the y-axis here. So y is equal to 0 here. So this is 0. And at these different locations, I can describe what is the total electric field as a function of y and time. Yep? That makes sense? Okay. So I'll tell you now that as a function of time, it's going to be kind of boring. It's going to be like cosine of omega t. Right? The electric field is just going to oscillate at whatever frequency it oscillates at. Now, if that's true, when you look at the light like this, does it look like anything's oscillating here? Not really, right? And actually, this one, I guess with the new battery, it doesn't do that. Actually, there is something oscillating here. Your eye just can't see. So something that's good to get used to quickly is that the light, the electromagnetic wave, it oscillates really quickly. The frequency of light, so optical frequency, it's somewhere from 10 to the 14 to 10 to the 15 hertz. Do you have some sense of how big these frequencies are? Like 1,000,000 gigahertz or terahertz. Do you know what the highest frequency is that you can visibly see with your own eyes that they are oscillating? It's flickering.
About
10 hertz? 40 hertz maybe. Anybody here know, anyone here know film, videos?
24.
So 24 frames per second is the videos that you normally watch, and your persistence of vision is enough that it looks smooth. So 24, so that would be what? Oh, frames per second, that is hertz. So when something is flickering at 24 hertz, you actually can't see it. These light, well, I'm not sure about the fluorescent light. When you look at incandescent light, some of the lights, they flicker at like 120 hertz, but your eyes won't see it. So the thing to get used to is that most of the time, when you are looking at intensity of light, you are going to be looking at a time averaged quantity. So here, the electric field here, yes, it is a function of time, but in the end, we don't really care about what it is a function of. We don't really care about the time dependence because it's going to average out. So, so what we really care about here is some kind of let me not write down the mathematical expression. I think it's gonna, let me write it down, but not bring too much attention to it. What you're going to be looking at here is you want the intensity as a function of y position, and what that'll look like is it'll be proportional to the time average. So time going from some 0 to t, 1 over t. And what you want to average is actually not the electric field, but the electric field absolute value squared. Something like that. I will skip over that for now. So what you really want to look at is, so the simplified version, we don't really care what the total electric field looks like as a function of time, because that's going to be boring. What we care about is how the total electric field look like as a function of y distance, as a function of position. Okay? So let's just get a quick sense of where people are. So it's a question of, as the light travels, let's look at an easy point first. Let's say, look at the point here. So after light goes through here, it's a wave that travels in many different directions simultaneously. So we are really looking at this wave as it's traveling to this single point. I'm not saying that it travels only to that point, but I'm only concerned with I'm only concerned with what happens to the wave as it's traveling along this line. There's a wave traveling elsewhere. I'm ignoring that for now. So what happens to the electric field what happens to the electromagnetic wave as it travels along this line? There's a sinusoidal wave. As a reminder, the electromagnetic wave, so I guess the wave representation of this electric field would look like E naught times cosine of, there's this omega t, but it's omega t minus kx, or I usually write the kx minus omega t, right? So if you imagine freezing the time, then it would look like some sort of wavy thing that appears here. And what that means is, as you look at different points here, the phase of the wave will change. It'll start from 0 phase to 0 to 180, 360, and so on. It does that many countless number of times. And when it reaches here, it has a particular phase. And as a relative phase from the starting point to here, would that relative phase depend on time? Let's say at this snapshot in time, it starts out here, and for the sake of argument, let's just say it ends here. So that would be the phase difference of, let's see, 180 plus 90, so 270 degrees, or something like that. If you looked at it at some later point in time, will this phase difference still be 270 degrees? Yeah. And that's an important thing to note right now as we make this more complicated. Because at some later point in time, imagine this wave moved on, so that it starts out from here. And at that time, the wave will have moved on here too, so that it ends like this. And the difference will still be 270 degrees. That even though when you look at the phase of the wave here, it'll be changing, the phase difference from here will remain stable, ideally. Okay? Now what I want to do, so this is the phase difference from slit 1 to screen. And what I want to consider now is the phase for the electric field that's arriving from the other slit. So for the electric field that's arriving from the other slit, this does the same thing. It starts out in phase, so goes like this. When I draw it, I'm going to mess it up. So before I finish drawing, let me ask. If it starts out phase of 0 here, what phase will this light arrive at here? Should be the same as the slit 1, right? So when you look at this, it should, let me just try to draw it right. Yeah, something like that. Knew I wasn't going to draw it right. So this was phase 1. The phase 2 would also be 270 degrees. So these two waves started out in phase, and they end up in phase on the screen. Let me ask you this question. Are these two waves always in phase everywhere on the screen? No, right? You saw with this double-slit experiment last time. You saw with this double-slit thing, you can't really see. Yeah, especially. Let's see, if I do it farther away, maybe you can see. Yeah, you saw with this double-slit thing that you do see darker fringes. That's where you get destructive interference. So you know that they are not always in phase on the screen. They do go out of phase. So what would cause electromagnetic wave from one slit to go out of phase with electromagnetic wave from the other slit? Like what could introduce this phase difference?
They travel different distance.
They can travel different amount of distance. So this point is actually special. This is the midpoint. So it's at the exact same amount of distance from either two slits. Because you see the change in phase as things travel over space, right? So the way this point, by the way, we call that point so that you have the language to describe this in. This is the point where we call something that we call central maximum happens. And the thing that's special about the central maximum is that's the point that's at exactly same distance from either of the two slits. So that's where they have to be in phase. Now, as you consider different points on the screen, they won't necessarily be at the same distance. And this is the argument that's sketched out in the textbook, and the one that I'll go through quickly to show you the geometrical argument. So this one, once you know to make it, this is actually easy, because we are making a bunch of approximations for this one particular line of argument. So I want to use what's already in the drawing here, this point here. That point on the screen is not at the same distance from the two slits. You can see that in the sketch itself, right? Okay, then the question is, all right, how much is the difference in that path length? And if you want to do exact geometry, it'll get complicated. So this is the picture I want you to imagine. Let me erase some of the stuff I drew because they are in the way. So this is what I want you to consider. So I'm going to imagine drawing an isosceles triangle. So like something like this. These two have the same length. Good? Then what I can say is that this distance is the path length difference. This is my delta x. Good? Now this is the approximation I'm going to make. This is lower division class. We only do, this is what's called the far field approximation. So in case you ever take the upper division version of this, this is called the far field approximation. And the approximation we are making is that this distance to the screen, L, is much greater than some reference length scale. What other lengths do you see in this diagram that I have not yet, I kind of labeled implicitly? D, right? The distance between the slit. Let me label it explicitly. So this is the only other distance scale you have. So when the distance to the screen is much larger than this distance, that's when we use something called the far field approximation in upper division. It's the only situation we consider, so you don't have to worry about the name. So under this approximation, this is what I can say. Can I say that whatever this angle is, it's going to be very small? Right? Then what I also can say is that whatever these two angles are, they're going to be approximately 90 degrees. So I can say approximately this triangle here is a right triangle. That makes the rest of my algebra so much easier. Okay? Let me point out a couple other simplifications that come out of this approximation. So for example, I can draw 3 different angles. I can draw angle theta 1 here. This is horizontal, and this is at how much angle above this is. And I can draw angle theta 2. And I can draw a third angle. Let's say, I don't like having these 2 different angles. So I'm going to instead choose to measure the angular position of the screen from the center between the slits, right? So I can do that. I can have this line here that I'm going to measure the angle of. Call this, I don't know, theta average. Yeah? Under this far field approximation, how do these 3 different angles simplify? Yeah, they're one and the same. So and that makes intuitive sense, right? If the slits are not very far compared to the whole distance, then when you actually try to measure them, they will end up being the same. So I'm going to just stick to using this. I'm going to stick to only using theta average, and I'll just call that theta. And when you look at this figure, you can kind of see how you would measure and express this theta too. You can express this theta as, one way to write this would be, well, I see this right triangle here. I have the distance. I have the height, or it's y position I'm considering. So I could say that this theta is the arctangent of y over L, or something like that. You've done enough trigonometry to know that. But now that I've defined the theta, how you would get it from some surrounding information, let me label the theta somewhere proper. I will label it here because it's going to make my life a little bit easy. Yeah? So I have a motivation for labeling the theta. So I identified this right triangle as helping me figure out some detail of this interference phenomena. So I want to know some of the angles of this right triangle. Good? With the theta defined this way, I can label the theta here just as easily, right? For a screen very far away, these 2, even though they don't look like it, these 2 are actually parallel. So these 2 angle thetas are the same. And once I've drawn this theta, then this is what I'm claiming. This is also theta. Okay? So all of this geometric argument is leading us to give us this expression. This path length difference is equal to, well, I have the hypotenuse, d. I have the opposite angle. So it should be d times sine theta. And all the other formulas you will see for double-slit interference, it comes out of these 2 things. One, the path length difference for path from in each slit to the particular point on the screen, and how this path length difference relates to phase difference. So we've been talking about phase, but I guess I never made it explicit how you go from the path length difference to phase difference. Some of you might guess this intuitively. It's I don't know. It depends on the person. I don't want to just say it's trivially easy because for some people it won't be. But if you have guessed this relationship that I'm going to spell out intuitively, then great. If you haven't, let me spell it out and see if that makes sense. So what I have is I have the difference in the space that it's going to travel. So I start out with the delta x. But I don't really want expressions of length. I want expressions of phase. So I want to refer it to some point on the cycle. So I don't really want the length. What I want is the length divided by the periodicity in length. So that would be the physical length divided by wavelength. That sounds okay to everyone? Okay. So this is giving me what fraction of a cycle this delta x is. If this turns out to be a 1/2, then I have half of a cycle. That would be actually the 180 degrees in phase difference. So that would be out of phase. If something is different by half a wavelength or half a wavelength plus an integer. In many of the formulas, you won't really want a fraction of a cycle. You want a phase angle. You want the degrees, or I guess radians. So here what I'm going to do is I'm going to take this fraction of a cycle and multiply with the 2 pi to convert it from cycles to radians. This is the kind of thing that's easy to miss because both the cycles and radians, they are fake units. There's no meters and seconds, and so you have to keep reminding yourself, this is a fraction of a cycle. Now that I have multiplied the 2 pi, now that's in radians. So this is the phase difference. This is the relationship between phase difference and the path length difference. Yeah? So in the general language we are going to use, this is what we can say. We can say you get constructive interference. Constructive interference when, so I want to express it in terms of the phase difference because that's going to be the common language you use for any interference. I want this phase difference to be, I guess 0 will work, right? What other angles will work other than 0?
2 pi, 4 pi.
2 pi, integer multiples of 2 pi, right? So it would be 0 plus 2 pi times n, where in the mathematical language, n is a member of, I guess it can be an integer that's, it's been so long. It can be negative actually, right? So, right? Yeah, so G is the set name for integer, right? It's been so long since I've used this language. Okay, good. So that's the constructive interference. So we don't actually need that 0 there. So let me actually rewrite it in a way that's more understandable. So we can say phi is equal to 2 pi times n, where n can go from 0, plus minus 1, plus minus 2, plus minus 3, and so on. Okay. In terms of some of the vocabulary you will see in the textbook, this is n equals 0 for the double-slit interference. This is the central maximum. That's the brightest spot you will see. And this plus 1, plus 2, plus minus 2, plus minus 2, plus minus 1, plus minus 2, plus minus 3, these refer to nth order maximum. So you might, your textbook might call this a first order maximum, or first order bright fringe. The other language you will see is the phrase bright fringe. But when you start counting orders, I want you to remember that it's counting what value of n this is. Okay? So that's for constructive interference. I guess the language gets a little bit more careful for destructive interference. Let me write it out first. So for destructive interference, so your delta phi should be, what's one value that works? Pi works, right? Does minus pi work? Yeah, minus pi works. Now does 2 pi work? Yeah, 2 pi, I mean 2 pi is this. Doesn't work. Minus 2 pi doesn't work. How about 3 pi? Works, right? So what it looks like is we want odd multiples of pi. So let me write it down this way. Plus minus 2n minus 1 times pi. I'm just being overly careful. I just want a general expression. And I'm going to say the n goes from 1, 2, 3, and so on. That covers all the possibilities that we are discussing. When n is equal to 1, I get 1 pi plus minus pi. When n is equal to 2, I get 4 minus 1, so 3 plus minus 3 pi. And the reason I'm writing it this way is because with this written out, this is what I can say. I can say this refers to the order of, I can say this refers to order of dark fringes. So when someone refers to the first order dark fringe or the second order dark fringe, third order, this is what they are referring to. Okay? So once you understand this role, the phase difference plays in interference, and once you understand this geometric consideration in double-slit interference, then the rest kind of follows naturally. Oh, let me derive the formula that's in your textbook. So you might see this formula in your textbook, which some people just memorize, and it's one of those formulas that you don't really have to memorize. So these are the formulas you will see in the textbook. D is equal to, let's see. You would see for constructive interference, you would see d sine theta is equal to m lambda, where m goes from 0, 1, 2, and so on. And for destructive interference, you would see d sine theta is equal to m plus 1/2 lambda, or do they use n at this point? Minus 1/2 lambda, where m goes from 1 to 3 and so on. Maybe they use n. No, I think n is used for diffraction. So you could look up these formulas in the textbook, memorize it, not knowing where they came from. What I was telling you before is where these formulas come from. So once you have this condition, then what you can do now is use your knowledge of the relationships between the phase and the path length difference, and the relationship between path length difference and the actual geometrical setup, d and theta. So let me call this 2. So using these two simple expressions that you could figure out just sitting at your desk on your own, once someone showed you what the right path was, you can go from this intuitive relationship about the phase difference to these formulas in a quick step. Let me just do that now so that you see it. So I guess it's just a matter of plugging it in. I have 2 pi n here. Let me plug, wow, this is confusing. That's not x, it's just multiplication. Let me just plug this in for delta phi. So you have 2 pi times delta x over lambda is equal to 2 pi n. The 2 pi's will cancel. Let me not worry about that for now. Let me plug in what delta x is. So you get d sine theta over lambda is equal to n. So you get d sine theta is equal to n times lambda. The exact same thing what you had from the book. And here, it would be the exact same thing. You have 2 pi times delta x over lambda is equal to this whole thing. Let me factor out 2. So you have n minus 1/2 times 2 pi. So 2 pi's will cancel again. Let me not worry about that. Plug in what delta x is. So you have d sine theta over lambda is equal to n minus 1/2, or multiply both sides by lambda, you get d sine theta is equal to n minus 1/2 times lambda, or the exact same formula that's in the textbook. So, I mean, if it's a matter of memorizing formulas from textbook, everyone can do that. I want you to start out with this, so that you don't get over fixated on these formulas. Here's what I'll tell you. These formulas, they are derived for a specific situation. They are derived for exactly this. Double slit, in air, slit separation, no other complications. Once you start adding complications, one of them that you will see as a challenge problem that I'm going to try to assign as a homework problem is what would happen? So we started out with the assumption that these two are in phase originally, right? What would happen if we made them out of phase? What would happen if we place a little glass plate here with some index of refraction so that light coming out of here has different phase than this? If all you know is this formula, then you are stuck. You have to do everything from scratch. But if you know these steps, then what you can do is you can start by modifying the phase relationship. You can say, all right, there's this phase difference that came from the path length difference, but maybe there's plus additional phase difference that's just added in for a different reason. And you can do the rest of the derivation. And once you cast everything in terms of phase, it's actually pretty simple derivation. So I want you to see that.